Okay, so we're going to dive into a paper that questions one of the most fundamental everyday tools in all of statistics, controlling for a variable. It turns out there's a hidden flaw in this practice that could be leading a ton of studies to completely wrong conclusions. Let's see how. All right, let's say you're a data scientist or maybe a researcher. What's the holy grail? It's finding a true causal effect, right? You want to prove that X actually causes Y, and it's not just some fluke correlation. It's pretty much the core mission in all of science. And what's the first thing we all learn to do? Well, you control for other variables. You think of all the other things that might be muddying the waters, we call them covariates or Z for short, and you toss them into your model. The whole idea is to statistically block out all the noise so you can see that one true relationship you care about. This is just standard practice. Now, this entire procedure rests on a massive assumption. It's called conditional ignorability. Yeah, it's a bit of a mouthful, I know. But the idea is pretty simple. It says that if you've been smart and controlled for the right set of Z variables, then your treatment, X, is basically random when it comes to your outcome, Y. It's the statistical magic that lets us pretend we ran a perfect randomized experiment, even when we couldn't. But here's the kicker. What if that bedrock, that very foundation we've built so much on, has a massive hidden crack? This paper argues that making sure this assumption actually holds is way, way harder than we've been led to believe. So check this out, because this is where things get really weird. On the screen, we've got two scenarios that, on the surface, look pretty much the same. You've got a treatment X and an outcome Y, and two variables Z1 and Z2 that you're controlling for. In scenario C on the left, everything works like a charm. But in scenario D on the right, controlling for those same variables gives you the totally wrong answer. So what on earth is going on? The one single difference is buried inside the very set of variables you're using to fix your model. In the safe scenario, your two control variables, Z1 and Z2, have nothing to do with each other. But in the dangerous one, they secretly share a hidden common cause. That's it. That one little invisible link, not between your treatment and controls, but within your controls, completely blows up the whole analysis. And this graph shows you just how bad the damage is. Look at the bottom row. That's our dangerous scenario. The real causal effect, that red dotted line, is negative. But because of that one hidden link between our controls, our model spits out a positive effect. Think about that. You're not just getting the number wrong, you're confidently telling everyone the exact opposite of what's true. So how big of a deal is this really? Well, the authors did the math, and for a set of n control variables, the number of potential hidden relationships you'd have to check for grows exponentially. We're talking on the order of 4 to the power of n squared. So with just 5 little control variables, you're looking at over 1 million possible hidden causal structures you'd need to rule out. It's completely impossible. Nobody can do that. This whole mess really gets at this tug of war between the two big ways we think about causality. On one side, you have the potential outcomes framework. It gives us that nice, convenient ignorability assumption, but it's a total black box. It doesn't tell you how to check it. On the other side, you have structural causal models, which give you these beautiful transparent diagrams, but they force you to specify every single little relationship in the universe. So you're stuck between a rule you can't really verify and a map that's impossible to draw. Let's try an analogy. The old way of doing things treats your set of control variables like a black box. You just kind of dump them into the model and cross your fingers. What this paper is saying is that we desperately need a diagnostic panel for that box, a simple set of warning lights on the outside that can tell us if the hidden machinery on the inside is about to go haywire. So, how do we build this diagnostic panel? Well, the paper gives us a really elegant solution. It's called the cluster causal diagram, or CG3 for short. Instead of trying to draw some crazy, complicated map of every single variable, this approach boils it all down to just 3 high-level practical questions. You just think about your treatment X, your outcome Y, and your entire collection of covariates Z as 3 big buckets. And you only have to ask yourself, could there be some hidden confounding going on between these big buckets? And once you answer those 3 simple questions, you end up with this beautifully simple diagram. It's just 3 dots. X, Y, and Z. The only lines you draw are these 2-headed arrows that represent any of that hidden confounding you just thought about. It lets you completely ignore all that internal complexity that was causing all the trouble. This new, simple diagram lets us check for a brand new, much safer condition the authors call structural ignorability. And the best part is, unlike the old school assumption, which was just some abstract algebra, this is something you can actually see. It's a visual, transparent check you can perform right on your little 3-node diagram. Okay, that's great, but how do we actually use this thing? How does this little diagram give us a clear green light or a red light on whether it's safe to move forward with our analysis? Well, the answer is you apply a classic rule from the world of causal graphs. It's called the backdoor criterion, but you apply it to your new, super simple diagram. It's basically just a visual test to see if there are any sneaky, hidden paths of confounding that connect your treatment and your outcome. And the test itself is incredibly easy. Let's go back to that scary scenario from the beginning. In that situation, we had hidden confounding between our treatment X and our control Z, and between our outcome Y and our control Z. Well, on this diagram, that creates a backdoor path that runs from X to Z and then over to Y. The test fails. Structural ignorability does not hold. The diagnostic panel is flashing bright red. But now, let's look at the flip side. Let's say you're confident there's no major hidden confounding going on between any of your 3 big buckets. Your diagram is totally clean, no arrows. That means there are no backdoor paths to worry about. Structural ignorability holds, the diagnostic panel is green, and you're good to go. It's really that straightforward. So let's pull back for a second. Why does all of this matter so much? It's really about a huge shift in how we do our work. It's about moving away from these opaque, faith-based assumptions and towards transparent, structural guarantees. So when you boil it all down, what do you really gain with this new approach? Well, for one, you don't have to specify some impossibly complex causal diagram anymore. Instead, you're just guided by 3 clear, high-level questions. You get to dodge all those hidden traps of the old assumption, and what you end up with is this practical, rigorous middle ground that makes doing solid causal inference so much more achievable for everyone. And that really leaves us with a critical question to ask ourselves about our own work. The next time you're about to control for a bunch of variables, just stop and ask, what hidden assumptions am I making about the relationships inside that set? What might be lurking inside your black box?